wash my cars.
I like looked at it and I was like, this is disgusting.
All right, so let's start on chapter 17 here. Now, you know, chapter 17 for some people is actually covered in 234. There's a historic reason for that, which I won't go into, but when I do it now, I do it in sequence, and we do 17 now. So if you've already seen this, that's good. I understand that I forgot to make the PDF of this available, and I really apologize, but I just forgot. If it ever happens, please send me an email and say you forgot. Okay? So, all right, alcohols and phenols. Alcohols are basically the organic equivalent of water. You have an oxygen with a hydrogen on one side, and you have something else on the other. Ethanol, classic example, OH, and an ethyl group. They share lots of the properties of water. They're going to hydrogen bond, they're going to be polar, they're going to dissolve stuff, whatever. Classic examples, this is beta-D-glucose. D refers to the absolute configuration. We have lots of OH groups all the way around. Ethanol, everyone's familiar with, I imagine. This is cholesterol. Cholesterol has an OH group down here in the first ring, and a big hydrophobic thing on this side. Common alcohols. We've all seen isopropyl alcohol, rubbing alcohol. This is 2-propanol is the same. Terbutyl alcohol, something we'll use in lab, maybe you used it last semester. It's actually 2-methyl 2-propanol. Glycerol. Glycerol is the backbone for lipids and fats. It is a triol, so 3 hydroxyls, 1, 2, 3 propane triol. Allyl alcohol. Remember, we've said many times, if you have a carbon adjacent to a double bond, that's referred to as an allylic carbon. So this is an allylic carbon bearing an alcohol, very reactive, very nicely reactive. Benzyl alcohol is also allylic because we have the equivalent of double bonds in the ring. Again, a very nice, very reactive alcohol. When we go to name them, we're going to look at the compound. We're going to select the longest continuous carbon chain that contains the alcohol group. So it must contain the OH. We're going to derive the parent name by replacing the E on the end with an OL. So ethane becomes ethanol. We're going to number this guy beginning at the end that is nearest to the hydroxyl group. So this means that the hydroxyl group is fairly high priority. So you want to try to give it the lowest number that you possibly can. Again, we're going to just simply number the substituents, write the name alphabetically. So not a whole lot difference. We're going to name it as an OL. We're going to number so that the OH group has the lowest number, and arrange substituents alphabetically. If we had a compound like this, we would look at it and say, what's our longest continuous carbon chain containing the OH? And it's going to be this guy. We're going to number this so that the OH group has the lowest possible number. Then we're going to look at substituents. Here at 4 and 5, we have methyl groups. We have an alcohol at carbon 2. So we'll put these things together. 4,5-dimethyl, 2, 6-carbon chain, hexane, all. Any question? Really pretty simple. On the next exam, you will have very basic, simple nomenclature of alcohols. And we'll go through some examples. Let's look at another one. Go ahead and quickly jot down on the back of your hand or something a name that you would give to this guy. Remember, you want the longest chain containing the alcohol. You want to give the alcohol the lowest number, and then list substituents alphabetically. Well, our longest chain here is going to be 1, 2, 3, 4 carbons, and it does contain the OH group. We're going to let this be carbon 1, so that could be 2. Now, as far as substituents go, carbon 1 has a bromine. So a 1-bromo. Carbon 2 has the hydroxyl group and a methyl. And then we have this ethyl group dangling out the end. We can name this very simply 1-bromo, 2-methyl, 2-butanol. So it's a but, 2-butanol, that's this guy. 2-methyl, 1-bromo, 2-butanol. Now, IUPAC has a couple different ways that are acceptable to name compounds like this. The simplest is what we just did here, 2-methyl, 2-butanol. It is also acceptable to split right here. Instead of saying 2-butanol, say butan-2-ol. That's also an acceptable IUPAC way. I think this is probably simpler and more intuitive. Any questions? Well, go ahead and jot down acceptable IUPAC names for these guys. We have 2 OH groups, so it's going to be a diol. It's a cyclohexane ring, so it will be a cyclohexane diol. The locations are carbons 1 and 3. So it's a 1,3 cyclohexane diol. And finally, both of these are equatorial. That means they're below the ring plane here, and they're both on the same side. So this is going to be cis stereochemistry. So we could call this cis 1,3 cyclohexane diol. Any questions? Now for this next guy. Our parent chain must contain the alcohol. So we see it's dangling out here on the side, right? It's on a 1, 2, 3, 4, 5 carbon backbone. So this is going to be a pentanol. The pentanol, the OH group is going to be in carbon 1. That gives it its lowest number. And then as far as substituents go, out here in carbon 1, 2, 3, 4, we have a phenol group. So putting this together, 4 phenol, 1 pentanol. Remember, your parent chain must contain the OH group. And that puts a phenol substituent in carbon 4. Any question? Our next guy is also a cyclohexane. Now, we have 2 methyl groups attached to the same position in the cyclohexane. Typically, you would look at this and say, this has to be carbon number 1. But the OH group must get the lowest number. So the OH, where the carbon where the OH is attached, has to be carbon 1. Which means that the methyl groups are in carbon 2, 3, 4. So we're going to have a 4,4 dimethyl cyclohexanol. You don't have to say 1 because automatically this has to be carbon 1 in the ring. 4,4 dimethyl cyclohexanol. Any question? All right, let's do a couple sets backwards. Go ahead and draw these structures. Now again, the simplest way that I think to do this is to start at the end and say this is going to be a 1-pentanol. So you have 5 carbons with an OH group on carbon 1. So this is carbon 1. We also have methyl groups in carbons 3 and 4. So that's 1, 2, 3, and 4. Carbon 3 and carbon 4. Start with the basic and then add your substituents. Cyclopentane, you draw a 5-numbered ring. It's a diol, so we have 2 OHs. Where are they? They're in carbons 1 and 2. Now you must also remember that these are going to be cis. So they must be on the same side of the ring plane. You could show this by drawing it in 3 dimensions, or you could use wedges. Wedges are probably simplest. Both hydroxyl groups are on the same side of the ring plane, and therefore they're cis. Any questions? Two-phenylethanol. So again, start with the end of the name. Ethanol. 2 carbons with an OH. On carbon number 2, we have a phenol. So, this is ethanol, isn't it? 2 carbons with an OH. We have to give the carbon bearing the OH the lowest number, so this is 1, this is 2, and we simply stick a phenyl group in that position. Any questions? One more set. Cyclohexane diol, 1-pentanol, and cyclohexanol. Fairly simple. Go ahead and jot down the roots and then stick in the substituents. Oops, sorry. All right, cyclohexane diol, 6-membered ring, 2 hydroxyl groups. Where are they? They're 1 and 3, and they have to be cis. Now, once again, you could draw a 6-membered ring showing axial and equatorial groups, or you could simply use wedges to show 1,3 cis stereochemistry. One pentanol is what we want to draw first. There it is. 1, 2, 3, 4, 5. And at carbon number 4, we're going to have a phenyl group. So that's 1, 2, 3, 4. Phenyl. And this is a cyclohexanol. So a 6-membered ring with an OH. And in carbon 4, we have 2 methyl groups. Any question? Yeah. No, it could be anywhere around the ring. You could put them both back, you could put them both forward, but they both have to be on the same side. That's cis. Yeah.
Do we have to show stereochemistry for the dimethyl cyclohexane?
No, you don't, because it's a plane of symmetry. Methyl's up and down, so it doesn't matter. All right, let's talk just a little bit about alcohols. The carbon in an alcohol, or the oxygen in an alcohol, is sp3. It has 2 lobes of electrons, and it has OH bonded to it, and then to something else. The dihedral angle here is about 109, so it's essentially tetrahedral. slightly off from pure tetrahedral. The electrostatic potential map for, well, this is methanol, or ethanol, looks something like this. We have the OH that is very, very prominently electronegative, lots of electrons, and then we're basically sucking electrons away from the carbon chain. The one thing about alcohols that they do well is they can hydrogen bond, just like water. This is methanol. They don't bond as well as water because one of the oxygen is busy holding on to the carbon. But still, we have fairly good hydrogen bonding. Because of that, if you look at the IR, you have a big, broad OH peak. Remember, that again comes from hydrogen bonding. And alcohols tend to be relatively high boiling relative to the carbon equivalent, and that's because we get all of this stabilization from hydrogen bonding. Alcohols are acidic, but very weakly so. We can write a standard acid dissociation equation. Alcohol plus water gives hydronium and alkoxide. You remember from general chemistry, we can write an expression for Ka, which is products over reactants. For ethanol, this equilibrium constant is very small, 10 to the minus 16. I remember water on a molar basis is 10 to the minus 15.7. So it's equivalent to the acidity of pure water on a molar basis. This is not very acidic. As you ionize this stuff, we're going to generate an anion, right? If you want to pull this equilibrium constant this way, to this side, what you want are substituents that will stabilize the anion. That is, you want electron withdrawing substituents. So if we start here with ethanol at about 16, as we put on things that withdraw electrons, this makes this more acidic. If we put something here that donates electrons, it makes it less acidic. For an example, let's look at ethanol and trifluoroethanol. pKa of 16 and 12.4. So about 10,000-fold difference in acidity. The reason for this is that the oxyanion here is going to be more stable when we have these fluorine groups. Basically because they're going to suck the electrons away from the anion and delocalize them on the highly electronegative fluorine. With ethanol, nothing like that can happen. These are ball and stick. Here's our trifluoro group. This is just a methyl. If we look at the electrostatic potential map, we actually notice something fairly interesting. Here is our carbon, here's our OH. You'll note that there's less red here than there is here. But because the fluorines are so electronegative and they're sucking electrons away, the dipole actually goes this way. In ethanol, the dipole is reversed. The electrons are sucked towards the oxygen. Here they're sucked towards the fluorines. Anything that stabilizes the anion makes it a stronger acid. Phenols. Phenols are basically a benzene ring with an OH attached. This is called carbolic acid. We talked about it earlier. It was the original antibiotic. You could spray it all over somebody undergoing surgery. They would get burned like mad, but it probably wouldn't die. And that was better. Again, this acid dissociation formed the phenol anion. Same equation, products over reactants. For phenols, phenols are much more acidic than simple alcohols. Here the Ka is about 10 to the minus 10 instead of 10 to the minus 16. Now we just talked about electrophilic aromatic substitution. We know there are things you can put on this ring that withdraw electrons, right? Well, if we look at an array, down here we have phenol itself at about 10. If we push electrons in, we go up. If we pull electrons out, we go down. Stabilizing the anion makes it a stronger acid. Any questions? Now, alcohols are very important in commerce, etc. You can make methanol at the rate of about 1.2 billion gallons by taking something called synthesis gas. Synthesis gas plus hydrogen will yield methanol simply. You make synthesis gas by taking coke. Now, coke is coal. You take cheap Illinois coal. You heat it in a vacuum. That drives off all the volatile stuff. And you're just left with carbon. You take this carbon, you burn it, react it with hydrogen, and you can make make methanol. Down in Gary, they've been doing this for a very, very, very long time. The only real problem with this is when you take coal and you cook off all the volatiles, what do you do with the volatiles? Well, what's in the volatiles? Oh, there are lots of phenols, there are lots of sulfur compounds, there are lots of really nasty compounds. What do you do with them? You dump them into Lake Michigan. Not a good thing. So that's one of the real problems with making coke from coal, is what do you do with the gum? These days they don't just dump it in the water anymore. There are more responsible ways to deal with the volatiles, but still it is a bit of a problem. Ethanol can be made fairly simply by the hydration of ethene. Turns out that there are gas wells in this world. You know, they spewed up natural gas, but some wells have a high concentration of ethene. If you take these at very high temperature, in the presence of steam, water, you can actually make 300 million gallons a year of ethanol. This is pure ethanol. And they are very, very paranoid about people coming in and out of their plants with buckets. So, now, because alcohols are weak acids, and because we're going to use alcohol anions in lots of different ways in chemistry, quite often it's easiest to convert them into the pure anion form. You can do that by taking something like, well, this is methanol plus sodium. We get sodium methoxide and hydrogen bubbles out. So this is just like adding sodium to water. You make sodium hydroxide, here we make sodium methoxide. Sodium amide, very strong base. This is the sodium cation the nitrogen anion. Very strong base. We dump these guys together. Again, we make the ion pair, and we bubble out hydrogen. We'll talk about alkyl lithiums later. This is essentially a carbanion, a methyl carbanion. Methyl lithium is a nice stable compound. You can get it in a bottle, dump it in with an alcohol, you make the alkyl lithium, alkoxide lithium, and of course methane gas. So if you need the alkoxide, this is a nice simple way to do it. All right, here we are back at 234. We know we can make alcohols by a number of ways. Everyone knows this, right? Every word I say is reviewed. We could take a simple alkene. We can hydrate it with aqueous acid. We know that this reaction involves a carbocation intermediate. Because it is a carbocation intermediate, it's going to be prone to rearrangement. And finally, we're going to get Markovnikov regiochemistry. Now what that means is we're going to form the most stable carbocation that we can here. And the OH group is going to add to that carbon. Carbocation, rearrangement, Markovnikov. Now this is actually a fairly brutal reaction. We can do a much more civilized reaction with mercury 2 acetate, followed by workup with borohydride. This reaction involves an intermediate mercurinium ion, not a carbocation. Because there's no carbocation, there is no rearrangement, but still we get Markovnikov regiochemistry. So again, here's our tertiary carbon, most stable carbocation. That's where the OH goes. We can do an anti-Markovnikov addition using borohydride, BH3 and THF, followed by workup with alkaline peroxide. This gives cis addition of the hydrogen and the OH group. Further, this is anti-Markovnikov regiochemistry. So the OH group appears adjacent to the carbon that would give us the most stable carbocation. That would be here. So the OH is here. And the last thing we should remember from 234 is if we have permanganate in an alkene, we can form a 1,2-diol. Now this is an intermediate manganate ester. And what that means, bottom line, is that both oxygens here came from the MnO4, and so they must be on the same side of the molecule. So we get cis addition and again a 1,2-diol. Any questions over everything you learned in 234? All right, today we're going to talk about other ways to make alcohols. We're going to do it by reduction. We're going to reduce it with either sodium borohydride or lithium aluminum hydride. Both of these are very nice reducing agents. We're going to take a carbonyl compound, add the molar equivalent of H- and make an alcohol. Borohydride or lithium. With aldehydes, we get primary alcohols. With ketones, we get secondary alcohols. We're going to also introduce something called a Grignard reagent. Grignard reagent is an organometallic compound. It'll be something, that's what the R is, that's something. Then a magnesium, and then a halogen. In a Grignard reaction, the something here, the R group, behaves as if it's an anion. The anion is simply going to add to the carbonyl, we're going to protonate it, and make an alcohol. This gives us secondary alcohols. This would, with a ketone, we would get tertiary alcohols. Very, very powerful way to do additions to carbonyls. And we're going to talk about all of these separately. So let's get started. Well, okay. I guess I forgot to push my button. Aldehydes and ketones were reduced by sodium borohydride or lithiol. Note that lithium aluminum hydride has to be done in ether. We'll see this is a problem in a minute. Ether has a boiling point of 35 degrees centigrade. You are 37 degrees centigrade. So it's really, really volatile. Not only that, but it's very flammable and explosive. So kind of a bad reaction. Grignard reagents add to halides and ketones. We'll see primary, secondary, or tertiary alcohols. All right. Let's start off with lithium aluminum hydride. The little purple ball here is the lithium. This is aluminum with 4 hydrogens, and it has a net negative charge. What's going to happen here is that one of these hydrides, that's H minus from the hydride ion here, is going to be donated to the carbonyl carbon. Now why? Because the carbonyl carbon is positive. It has a distinct positive charge. Oxygen is more electronegative, pulls the electrons up, and makes this a positive center. So we're going to take the hydride, that's a hydrogen with its electrons, 2 of them, and it's simply going to add to the carbonyl carbon. When it does, you form this intermediate. An O minus where the carbonyl was, here's the hydride we just stuck on. Now you take this and you dump it into water, and presto, you have your alcohol. Now lithium aluminum hydride is one of the most versatile reagents that you could ever imagine. It really is. Lithium aluminum hydride reacts with nitriles to give amines, with epoxides to give alcohols, with aldehydes, with ketones, with esters to give tertiary alcohols, with 3 nitrogens, azides, with azides to give amines, with carboxylic acids to give alcohols. It's a very, very, very versatile reagent. Problem with using lithium aluminum hydride, in spite of the fact that it is so wonderfully selective, so wonderfully powerful, and the selectivity can be shown here. Here we have a conjugated ketone. If we do a lithiol reduction, we get 94, 95% of the alcohol and just a little bit of the over product. If we did borohydride that also adds H minus, we get darn near 50-50. So this is a much better reagent. And it just does everything. It's wonderful. Why will you never use lithium aluminum hydride in this lab? Because it's more selective, but this contains a tiny drop of water. Let's see if I can back it up and make it start over. We have a flat or a beaker with a tiny drop, one drop of water in it. I have another beaker that has lithium aluminum hydride in ether. Dump them together. Now, poof. Even if your ether isn't 100% dry, when you go to mix this stuff together, this is what you get. It really, really is an obnoxious stuff to work with. Very flammable, explosive, not fun. Sodium borohydride is much more fun. Does the same thing, not quite as well, but my goodness, you can dissolve it in water. Let's do some quick problems. If we wanted to make these alcohols, what carbonyl compound would we start with? Now, as you look at the products here, what should be going through your head is, where this oxygen is attached, well, that used to be a carbonyl. And all in the world I've done is add H- to the carbonyl carbon. So what you want to do is draw the whole skeleton and just make this a carbonyl carbon. So for our first guy, we're doing a lithyl reduction. That means this used to be a carbonyl, a methyl, and a phenol, and it simply looked like that. All we did is add H- to this carbon. That made this the OH. We don't show the H, but we all know it's there. Simple hydride reduction. Same thing here. Oxygen is bonded here, right? That used to be a carbonyl. So simply redraw the entire structure, making this a carbon-oxygen double bond. And it should look like this. Simple ketone, methyl ketone. Here we have a 6-membered ring with an OH in it. This used to be a carbonyl, didn't it? So it was a cyclohexane only. We'll do nomenclature in chapter 18. Cyclohexanone. So this was a carbonyl, and it just looked like this. Now, we're making a chiral center here. Yes, we will get both stereoisomers. So it will be a racemic mixture at this carbon, top or bottom. This one would probably predominate because the product, they're both equatorial, they're more stable. Any question? Whenever you see borohydride or lithium aluminum hydride and a carbonyl compound, just think, I'm going to add H minus, make the carbonyl carbon an OH. Got it? Let's go on to Grignard reagents. Grignard reagents, kind of interesting. If you take a simple alkyl halide, dissolve it in diethyl ether. Again, ether, this problematic solvent, but we're going to dissolve it in there. And then we're going to add magnesium metal. Little chunks of magnesium, just add it in there. What happens is it'll fizz and it gets hot. You have to make sure you cool it as you do it so it doesn't go nuts on you. When you're done, you get something called the alkyl, whatever the group was, magnesium halide. That is a Grignard reagent. The thing that's neat about a Grignard reagent is that this carbon here that's bonded to the magnesium, that's going to pretend that it's a carbanion. It's going to act like it's a negative carbon. If we do this with bromobenzene, again, magnesium, diethyl ether, by George, we get phenol, magnesium bromide. Very reliable reaction. Now, why do we have to do this in diethyl ether? Doesn't have to actually be diethyl ether, but it has to be an ether. The reason is that the ether actually participates in the reaction. This is methyl magnesium bromide by itself. This is methyl magnesium bromide bonded to two diethyl ethers. This is the Grignard reagent. This is not. Now remember, we want this carbon to behave as an anion. We can look at here's our methyl magnesium bromide. We can look at the electrostatic potential maps. Here's our methyl group. Here's our bromine. This is kind of a pale, ugly army green, right? If we want a carbanion, we want much more red. If we do the electrostatic potential map on the complex here, look at our methyl group. It's so much more red than it is here. By chelating in these 2 moles of ether, this increases the electron density here a whole lot, and that's what makes the Grignard reaction work. When you see a Grignard reaction, think, take the anion, the methyl anion here, and simply add it to a carbonyl. Just like we did H minus, here we're going to do carbon minus. Here's our generic Grignard reagent. The R group, that's our carbon, is negative. Here's our carbonyl. Remember, this is positive, more positive than that end. We're going to simply donate R minus here and form this addition intermediate. The Grignard reagent is a stabilized carbanion. Once we have this stuff, it's stable. We take it down, we dump it into water, and we make our product. Things that we will see about Grignards. If we take a Grignard reagent, we can react it with formaldehyde, that's 2 hydrogens, to get primary alcohols. Aldehydes will give us secondary alcohols. Ketones, tertiary. Esters, interesting, also give us tertiary alcohols. So let's run through all of these. Very simple. Here I have formaldehyde, and I have cyclohexane magnesium bromide. Go ahead and jot down the structure of what we're going to make. Remember, this is going to behave as a cyclohexane anion. This negative carbon is simply going to add to the carbonyl carbon. When it does that, we will get this addition intermediate. And when you're done, you take this whole mush and you dump it into dilute acid. When you do that, you wind up with the corresponding alcohol. Formaldehyde plus a Grignard, primary alcohol. Any question? An aldehyde. Here we have 1, 2, 3 carbons. This is propyl magnesium bromide. Same thing is going to happen. This carbon thinks it's a carbanion. It's going to attack the carbonyl and make this an O-. The product will have a methyl group, a hydrogen, and this 3-carbon chain. Methyl group, oxyanion, hydrogen, and our new 3-carbon chain. Think about this in terms of synthesis. When you want to do a synthesis, you want to build a molecule, right? Here we are adding big chunks of stuff to simple molecules. This is how you do synthesis. Once we get the oxyanion, all we do is wait for a little bit, make sure it's cool, dump it into aqueous acid, and we get the corresponding alcohol. Once again, the methyl group came from here. We have a hydrogen here from that, and there's a 3-carbon chunk that we just added. Isn't this kind of neat chemistry? I mean, we're just putting stuff together and making big stuff out of it. Next, of course, is a ketone. Let's do a ketone. This is methyl ethyl ketone. And here I have methyl magnesium bromide. We all know what's going to happen. The methyl group thinks it's a carbanion. It will attack the carbonyl. On this carbonyl, we will have 2 methyls and an ethyl. The carbonyl will be our O-. Once we have formed this stuff, simply dump it into acid, and we make our tertiary alcohol. The methyl and the ethyl came from our original ketone. And then one of these methyl groups is what we added from our Grignard. All right, I'll hush for a second. And just quickly, give me the products here. We have cyclohexanone and we have methyl Grignard. We're going to do methyl group, simply going to add to the carbonyl carbon. This will be an O minus, and we're going to protonate it to make our tertiary alcohol. There's the addition product. Second step is always to dump it into aqueous acid carefully. And we have made 1-methyl cyclohexanol. Any questions? This last lab we dealt with benzaldehyde, didn't we? If we take benzaldehyde and react it with methyl Grignard, write the product. It's going to react as a methyl anion. It's going to add to the carbonyl carbon. So on the carbonyl carbon here, we will have a methyl, hydrogen, and an O minus. Really does get to be simple after a bit, doesn't it? Here's our methyl that we added. Hydrogen was there. And there's our carbonyl carbon that's now an O minus. We dump this little guy into water, and we get 1-phenyl ethanol. When we name this guy, we have 2 carbons, that's 1 and 2, so it's an ethanol with a phenol group in carbon 1. Let's do one more. Let's just take phenyl magnesium bromide and acetone. Here we're dealing with a phenyl anion. So a benzene ring that thinks it's a negative charge is going to attack the carbonyl. On the carbonyl carbon, we are now going to have 2 methyl groups and our benzene ring. Carbonyl is going to be an O minus, and it's going to look like this. 2 methyl groups and a phenyl. When we finally dump it into water, we're going to protonate the O minus, and we will make This is a 1, 2, 3, so it's a propanol, right? It's a 2-phenyl propane 2-ol. You could also say 2-phenyl 2-propanol. Now, isn't the Grignard reaction just kind of neat? You can just stick stuff all over it. This quiz that we're going to take after spring break, after we do chapter 18, is going to deal with basically Grignard chemistry. Going to have a lot, well, we'll see some examples of what we're going to do, but there are going to be lots of them, just simple Grignard chemistry. Let's go ahead and do some just for practice. Go ahead and quickly jot the products for each of these guys. Our first one here, we have bromomethane in the presence of magnesium and ether. What are we making? We are making methyl magnesium bromide. That's a Grignard reagent. Once we make that, we dump in benzaldehyde, do our reaction, work it up with water. The methyl group is going to add to the carbonyl carbon, and we will get this. Now, I've colored it for your convenience. All of these carbons and oxygen came from the benzaldehyde, and here's the methyl group that we just added. Here we have bromobenzene, magnesium and ether. What are we making? Phenyl magnesium bromide. Phenyl group is going to act like a carbanion. It's going to attack the carbonyl. We will have an OH here, 2 methyl groups, and our benzene ring. This is from the acetone. This is from the benzene. Here's the bond we made. This is 2-bromopropane in the presence of magnesium and ether. We're going to make the isopropyl magnesium bromide. That's our Grignard. This carbon will think it's a carbanion. It will attack the carbonyl. Now, realistically, it can attack from the top or the bottom, can't it? If you were an isopropyl group, I think it would probably be easier to attack from the bottom because this methyl might be in the way. Probably this would be your preferred product. Again, the pathway to the carbonyl, methyl sticking up, we can sneak in the bottom. This is probably the preferred product. This comes from the isopropyl, and all of this from our ketone. Any questions? Now, you know, a whole lot about organic chemistry has to do with symmetry. Remember, we talked about symmetry everywhere. Way back when we did chiral centers, and we talked about it in NMR and IR and whatever. Symmetry is important, right? The Grignard reaction has an inherent symmetry to it. Oh, okay, we've already done these. Oh, maybe we haven't. Well, anyway, we know how to do these. Let's talk about Grignard reaction and symmetry. If we look at an alcohol, this is a secondary alcohol, that's a hydrogen. We could make this by two possible pathways from a Grignard reaction. Two. There's symmetry here. How do you do this? Well, you look at the carbon bearing the OH, and then you just simply split on both sides. If we split here, we could say that this is the group we added. If we split here, this is the group we added. So we could make this by two Grignard reactions. Let's start off this way. We're going to look at this, we're going to split it on one side or the other. And we're going to ask ourselves, if we did that, what would the Grignard reagent be? What would the carbonyl compound be? Let's split here. Now, the half of the molecule with the OH used to be the carbonyl, right? And the other half was our Grignard. So, what was the Grignard? It was just a phenol group. So that would be something like phenol magnesium bromide. How about the carbonyl half? Well, it's this whole chunk of molecule, except this was a carbonyl. So we could write it like this. Bromobenzene, in the presence of magnesium and ether, makes phenyl magnesium bromide. This carbon used to be a carbonyl, got a hydrogen on it, it's an aldehyde. Mix these two together, and we make that. Let's do the other side. Split on this side. Write down the carbonyl and the Grignard you would need to make that splitting on this side. I will pause for a moment. Oops. Now, this half of the molecule was our carbonyl, right? Carbonyl compound. This was a carbonyl carbon. There's a hydrogen attached and a benzene ring. What is that? That's benzaldehyde. Smells like cherries. This half. This used to be our Grignard reagent. It's 1, 2, 3, 4 carbons. This was our alkyl halide carbon that's now a carbanion. And the pair would look like this. This is a 1, 2, 3, 4, so it's a propane, 2-bromopropane. Magnesium and ether makes the Grignard. Add it to benzaldehyde, and you make this stuff. Make sure this makes sense to you, because on the quiz, on the exam, for the rest of your life, you will see questions like this. Take this molecule, split it, show me 2 pathways to make a Grignard reaction. Now that I said that, let's do it again. Take this, show me 2 pathways to make this compound by a Grignard reaction. Find the carbon bearing the OH. Split on one side. That will give you the Grignard on one side, the carbonyl on the other. Split on the other side, you get another pair, and we'll see what they look like. So let's split. Let's split on this side. Our Grignard reagent was this half. It had 2 carbons, right? That's an ethyl group. So ethyl magnesium bromide, or ethyl bromide. The other half, we have 1, 2, 3, 4 carbons. This was an aldehyde, because it's a secondary carbon. So we have an aldehyde, we have this 3-carbon chain attached. That should work. To the other side. Now our Grignard part has 1, 2, 3 carbons. So this was 1-bromopropane. The other half here, this was an aldehyde, CH2, CH3. And it simply looks like that. I assure you, after a while, this really gets to be fun. Any questions? Now, initially, one of the most confusing things to students about Grignard reactions has to do with carboxylate esters. Because looking at the product and trying to figure out how you got there can sometimes be tricky. So let's look at a Grignard with an ester. This is methyl acetate. We're going to react it with methyl magnesium bromide, 2 moles of it. And by George, we wind up with a tertiary alcohol, terbutyl alcohol. Again, this can sometimes be a little difficult for people to grasp. But let's think about this stepwise. Here's our ester. We're going to take and we're going to react this with a Grignard. Remember, the R group here in the Grignard thinks it's a carbanion. It sees this positive carbonyl carbon, and so it attacks. And here's what we get. Now, we could all do that, right? We all understand that so far. However, this intermediate is different. We're going to do a lot of this in chapter 20. But this tetrahedral intermediate has a leaving group. A leaving group, something it can take its electrons and go home. It's going to go. Just going to take its ball and go home. That is the OR group. If we move these electrons in to make a carbonyl again, these electrons can go back to the OR, and you make a carbonyl, and OR minus simply floats around in solution. It's a leaving group, it left. Well, now what have we made here? We made a ketone, right? What do ketones do in the presence of Grignards? Well, they react. So another one of these guys wanders up. The R group is going to attack. And now we have, after we dump this into acid, a tertiary alcohol. This thing here is what we started with, and we've added 2 of our Grignard R groups. When you react an ester, whatever is attached as the OR is gone. Gone forever, you're never going to see it again, poof. Only thing that's going to survive is what's attached to the other side. It could be a carbon, could be a hydrogen. And then we're going to get 2 R groups from our Grignard. Now that's kind of a neat reaction. We'll come back to this in just a little bit. But let's just finish up talking about the downside of Grignards. Limitation. Remember, we're dealing with a carbanion, right? Really strong base. If your molecule has any hydrogen in it that's acidic, won't work. Carbanion is just going to pull the hydrogen off, in this case methanol, pull it off, make methane, and your reaction is dead. So we can't do a Grignard if we have acids, alcohols, amines, amides, or thiols. Won't work at all. Secondly, if we have mixed functionality, because we have a really strong nucleophile, it can add to darn near anything. Not just carbonyls. It can add to nitriles, nitro groups, sulfonyl esters, whatever. So if you have any of this other stuff in your molecule, you can't use a Grignard. Now there's a way around this guy that we'll talk about at the end of lecture, but the rest of these pretty much are limitations. Now, on the quiz that we're going to do after we bask in the sunshine over spring break, there are going to be synthesis questions that are going to look like this. You will be given a selection of compounds, and it will say utilizing any of these and whatever else you need, make this stuff. All right, let's do this. Any questions? Let's do this. If we look at our product here, we have a 3-carbon chain, a 3-carbon chain, and something in the middle, right? So right away, we can rule out cyclohexanone. That makes sense. To do a Grignard, we need a carbonyl. So this isn't going to work, that's not going to work. This might, not that. This guy is a 5-membered ring. Not here, that doesn't work. Benzene ring doesn't work. No carbonyl, that's an alcohol. And this has a carbonyl, it might work. So right away, you look at the whole selection and you narrow it down to possibilities. All right. What have we got for carbonyls that might work? Really, it's just these two, isn't it? So we're dealing with 2 of them. Can you make this molecule, this guy, starting with either of these? Well, by George, they're both esters, aren't they? And what did we just talk about with esters? We said with an ester, we're going to add 2 Grignards to it, right? 2. If we took this guy and we added 2 moles of Grignard, we would have the original propyl group and then 2 other things dangling out. Here we only have hydrogen and 2 things. Here we would have, remember we're going to lose the O whatever, we would have a hydrogen and we could add 2 things to this carbonyl. 2 things. So my bet would be we could make it starting with this. So if we start with this, what Grignard reagent would you need? Remember, we're going to add 2 of them. This is a tertiary alcohol. This would give a secondary. Going to split our molecule here. Remember, we're adding 2. So we're going to split on both sides of our carbonyl, like that. The 2 wing portions both came from Grignards. And the little guy in the middle, that's our CH carbonyl from our ester. So this is our starting material. Write down quickly while I pace the Grignard that you would need. Well, if our Grignard has 1, 2, 3 carbons, it had to have a halogen attached, right? Bromine or something. So that's going to be a bromopropane. 2 propyl magnesium bromides, and 1 of these guys. Going to lose the O-ethyl. It's gone down the drain, poof, off to Iowa. Add our 2 propyl groups, and we have this compound. Any questions? Now again, your quiz is going to have like 5 or 6 of these. Gonna be lots of fun. All right, well, let's deal with another organometallic compound. Instead of using magnesium, I'm going to take an alkyl halide and react it with lithium metal. When I do this, I will make what's lovingly called an alkyl lithium. Now, the thing about an alkyl lithium is that this is a very, very polar covalent bond. And just like a Grignard, this end of the molecule, where the carbon is really negative. And it's a good nucleophile. So even though we're changing from magnesium to lithium, the chemistry is going to be the same. This could be up to tertiary, alkyl, aryl, or vinyl. I mean, this just is really, really versatile. The reaction of alkyl and aryl and vinyl lithiums with carbonyls. So here we have our negative R group. Here we have a carbonyl. We all know what's going to happen. R minus is going to attack. We're going to make the addition product. We're going to dump this into aqueous acid. And whoops. And we will simply protonate this to make the alcohol. So let's look at a real example. I said this worked on alkyl, aryl, and vinyl. How do we make this? Well, this used to be a bromine. We react 1-bromoethene with lithium, and we make this stuff. Now, believe it or not, this actually works. This thinks it's a carbanion right here. And it's going to form a bond with the carbonyl carbon. When it does, simply attacks the carbonyl. We have added our double bond. This is the bond we just made, right here. Here's our carbanion that was right here. We added this, we made our bond. Isn't this an amazing reaction? Again, the whole point of organic synthesis is to make amazing compounds. And this is kind of a really neat reaction. We simply take our stabilized anion, add it, form a bond. The tough part here is recognizing that this is a new bond. This is what we had, this is our new bond, and we now have an OH. Any questions? This is kind of an exotic example. Let's do some that are more mundane. Go ahead and quickly draw the products of these addition reactions. Now this is a mixture of lithium, alkyl lithiums, and Grignards. But the chemistry is exactly the same. We're talking about taking a simple stabilized carbanion, adding it to a carbonyl carbon, and then making it an alcohol. Our first one, our methyl group is our nucleophile. It's simply going to add to the carbonyl carbon. The carbonyl carbon will now be an alcohol with a methyl, a hydrogen, and another methyl. It will be 2-propanol. Our next one quite simply is a Grignard reaction, isn't it? Here, our anion is simply the benzene ring itself. It will add to the carbonyl carbon. We'll make an alcohol. This will have a hydrogen and 2 benzene rings. Our third one, we're dealing with formaldehyde, 2 hydrogens. Same thing is going to happen. The carbanion will attack. This will be an OH with 2 hydrogens bonded to this stuff. Questions? Well, let's do another set. I'll hush for a second. You want me to go back?
Yeah, can you go for it?
I guess I could.
The hydrogen, is it coming from the H3O plus?
Nope. The hydrogen on the OH, yes it does.
Okay.
Both of these hydrogens come from the formaldehyde.
So, question. For that ester, is it going to be the same when used to alcohol?
Yeah. Let's look at another set. These are all Grignards. Now remember, our first one is an ester. What do we do with the alcohol half of the ester? We wash it down the drain. Doesn't matter what the alcohol portion is, it's gone. We're going to keep what's on the other side, that's a methyl group. And we're going to add 2 of the methyl magnesium bromides. So we'll wind up then with 3 methyl groups and a tertiary alcohol. 1 methyl we started with, 2 more that we added. Now this next one everybody misses. So it's always on the exam. The trick here is figuring out where you're going to make your bond. What did this used to be? It used to be a triple bond, so ethyne bonded to a bromine. So what are we going to add? We're going to add the 3-carbon double bond. The triply bonded unit, ethyne. We're going to add that to our carbonyl. So this carbon here, right here, this guy, thinks it's an anion. It's going to reach over and attack here. We will now have our triple bond dangling down here, and it will look like that. And our last one is a vinyl lithium. Once again, just think to yourself, what is the carbanion? Pull the lithium off, pull the magnesium off. This is a negative charge right here. That electron pair is going to form a bond. It's simply going to attack acetaldehyde, and when it does, you'll make this. Here's the methyl from acetaldehyde, the hydrogen is here, it's an OH now, and this is the chunk that we just added. Work a bunch of problems. This is actually fairly simple once you get the hang of it. Identify the anion, add it to the carbonyl. Any questions? All right, let's go back to chemistry 234. Reminisce about the good old days, right? When life was simple. How do you convert an alcohol into an alkyl halide? Again, this goes way back to chapter 6 or something like that. It's a simple acid-catalyzed SN2 reaction. Simple bubble in HCl, we're going to protonate this guy, it makes it a leaving group, chloride attacks, and we get the corresponding product. Now, in general, this is going to be an SN1 style reaction. SN1s are bad because they have carbocation intermediates and you can do rearrangement. You can make alkyl halides this way, but it's not great. There are better ways to do it. We're going to look at 3. If you take an alcohol and react it with phosphorus tribromide, what happens is you make a phosphorus ester, a tribromo phosphoester through the oxygen. That kicks out a Br minus. The Br minus can then attack in an SN2 style to give you a very nice, clean alkyl bromide. So the steps look something like this. Step 1, we're going to take our OH group, attack the phosphorus, and bromine leaves. So we get this, phosphide ester. Now, this, once again, is what we call a leaving group, isn't it? Br minus is a nucleophile. Leaving group, nucleophile, think SN2 reaction. Now, what do we know about SN2 reactions? Chapter 5. They go with inversion of stereochemical conformation. It's a backside attack, inversion of configuration. So if we started off with a chiral compound here, say this was R, we did this, this would be S. Stereochemically pure. It's an SN2 reaction. Once again, PBr3, make the ester, do the displacement, inversion of configuration. There's another way we could do this. SOCO2, that's thionyl chloride it's called. It's really nasty stuff. Don't go around sniffing it. And this is pyridine. Let's pretend that this is also a chiral center. This is going to react the same way that PBr3 did. The oxygen is going to attack the sulfur, chlorine's going to leave. This is pyridine. Pyridine is a heterocycle, it's aromatic. It stinks, but it's aromatic. Figure that one out. We add this to our sulfur and lose a chlorine. Now, just like PBr3, this is a leaving group now. This is a nucleophile. SN2 reaction. Again, inversion of stereochemical conformation. SN2 inversion. But the really neat thing about doing thionyl chloride is that you can actually control the stereochemistry here. If you're trying to do some elegant synthesis and you want a particular conformation, you can do that with thionyl chloride. With pyridine, which is polar, we get inversion. But if we do this same reaction in something like hexane, that's nonpolar, we can't make ions. Hexane doesn't do ions very well. It's going to add, make the same sort of stuff, but once you get this, we do this magic reaction. And this is probably the only example you'll ever see in organic chemistry. It's a front side attack. Remember, SN2 is always backside. This is a front side attack. What happens is the chlorine just kind of slips over as this bond breaks, called an SNI mechanism. And by gosh, we get retention of configuration. So if you start with R, you wind up with R. You start with S, you get S. So with thionyl chloride, depending on your solvent, you can ultimately control your stereochemistry. It's a real touch of elegance to your synthesis. Any questions? All right, another thing that we learned a long time ago was that you could take an alcohol and you could do dehydration, dump it into sulfuric acid, and by gosh, you can make an alkene. This is yet another example of a 234 grade reaction. It's terrible. It's a horrible reaction. You do this, you wind up with a pot full of tar. Carbocation intermediate, we get rearrangements. It's Markovnikov, but it doesn't really work very well. We're in 235 now. We're big guys. And we can do this better. If we use POCO3 in pyridine, we get beautiful chemistry. We make a double bond where it's supposed to be. We don't get rearrangements, and we don't get black tar. What happens here is the OH is going to attack. We're going to make our ester just like we did with PBr3. Except now, pyridine is going to be a base. Pull off a hydrogen. This stuff is going to leave. And presto, we get the site Ceph. It's the most highly substituted alkene. Works really nice. Again, it's a smooth reaction. No real problems. Any questions? Another class of reactions we want to talk about are oxidation. If we have an alcohol and we want to make a carbonyl, how do we do that? there are two reagents we're going to deal with. One is pyridinium chlorochromate. That's this stuff. And the other is going to be just chromate itself, also called Jones reagent. Jones reagent is cleaning solution. You dump this stuff in to clean out the gunk. Pyridinium chlorochromate, however, is like magic. It's really nice reagent. Here we have a primary alcohol. With PCC and dichloromethane, we oxidize this smoothly to the aldehyde. Now that's magic because aldehydes are very sensitive. Aldehydes want to be carboxylic acids. But PCC is mild enough, it does it beautifully, and we get only the aldehyde. If we did Jones reagent with this particular compound, we would get the ketone. Aspartic acid and sulfuric acid, once again, is a very powerful oxidizing agent. If we compare PCC versus chromate for this, again, we would go all the way to carboxylic acid. PCC stops it at the aldehyde. There's one more magic reaction. MnO2. MnO2 and pentane of all things. MnO2 is this dirty black solid. Okay, it doesn't dissolve in anything. But if you have an allylic alcohol, so this is adjacent to a double bond, and you put it there in the presence of MnO2, again, you make the aldehyde almost like magic. Aldehydes are tough to make in chemistry. So these things are actually very important. Let's just run through a bunch here. If we took benzyl alcohol and Jones reagent, what would we get? Remember, Jones reagent is rough. It doesn't stop at the aldehyde. It will take it all the way to the carboxylic acid. So what we're going to wind up with is a benzene ring. This carbon is now a carboxylic acid. Here's a primary alcohol with PCC. PCC is wonderful stuff. It will oxidize it to the carbonyl, but stop at the aldehyde stage. So what we get is the same basic molecule, except that this is now a carbonyl. Now if we have a secondary alcohol and we do Jones reagent, don't have to worry about it making a carboxylic acid. In fact, this will work fairly nicely. It'll stop simply at the carbonyl. Here we go from the secondary alcohol to the ketone. Yeah.
Are there any other combinations of chemicals together that can make these reagents, or just like specifically those will give us
Typically PCC dichloromethane, that's what you're looking for. Pyridinium chlorochromate dissolves nicely. Dichloromethane experimentally is easy to get rid of, high vapor pressure. this is what you use them at. Do another set here, kind of mix them up. Here we have a secondary alcohol. We're doing PBr3. What does that do? Step one, we make the ester, right? Step two, we're going to do backside displacement, SN2, with Br minus, and we'll simply make bromocyclohexane. Now here's a good test question. Here I put stereochemistry in, right? We have a methyl coming forward, which means the hydrogen is going back. And we're doing thionyl chloride impurity. This is going to give us the alkyl chloride with inversion of configuration. So how do you show that? If we have inversion, if our methyl used to be pointing forward, it's now going to be pointing back. That's all you have to do. If we have inversion, we're simply going to swap the orientation of one of our groups. This was forward, now it's back. That's inversion. Straight 234 stuff. Simple one here. We have an alcohol, we have PBr3. What are we going to do? No stereochemistry to mess with. Oh, here, I just put this in just to show you. There's a hydrogen here. It's pointing back. Over here, we've inverted, so the hydrogen is pointing forward. All you have to do is show any one group inverted, and that works. Here, we're just taking the alcohol, making an alkyl bromide. How simple is that? Let's do another set. Mix them up again. POCl3 and pyridine, PBr3, HCl and ether. With POCl3, what are we doing? We're going to make a double bond, aren't we? We're going to make a double bond. So this is going to react with the phosphorus. This is our leaving group. Our double bond is going to form right here. It's going to look like that. Really nice, clean E2 elimination. No rearrangement, no nonsense. It just works. Oh, we have stereochemistry again in PBr3. What does PBr3 do? Gives us an alkyl bromide. What's our stereochemistry? Inversion. So draw this as the alkyl bromide with inversion. Question. We're we're going to stick a bromine here. I have this coming forward. It's got to go back. That is inversion. This goes all the way back to 234, HCl and ether. Why does this work? Because we're making a benzyl carbocation. You can't get much more stable than that. No rearrangement's going to happen. We're simply going to add the chlorine to this spot. Whoops. Or we could do an each one elimination. I guess I should have read the slide better. This could give us the alkyl halide, but again, since it's a carbocation intermediate, we can also get a parallel E1 elimination, and that's what I've shown you. This won't be on the exam. Two more. Primary alcohol, PCC. Primary alcohol, chromate. Your quiz will have an assortment of reactions that cover all of these just like we've done. It's amazing. I can just come up with reactions all day. Remember, PCC is special because it will stop at the aldehyde stage. That means we're going to make this a carbonyl, has a hydrogen attached. It will simply be the aldehyde. And our second one, Jones reagent. Powerful oxidant, will not stop at the aldehyde. This carbon will become a carboxylic acid. Any questions? All right, let's talk about the problem with Grignard reagents. And we're going to introduce the concept here of protecting groups. Now remember, Grignard reagents will react with anything acidic. If you happen to have a complicated molecule with something acidic in there, it will. An example. If we wanted to make this into a Grignard reagent, we couldn't. Because the OH here would simply react with the Grignard reagent itself. If we tried to do this, it would decompose instantly and nothing would happen. What we're going to do here is look at two strategies to block the OH that will then be easily recoverable. The first, going to react it with trimethylsilyl chloride. Now here, the silicon is our central atom. O- is going to attack, chloride will leave, and we'll make this stuff. It's a silyl ether. Now as long as you don't breathe on it or do anything funny with it, it's stable. Now we can take this and do Grignard chemistry here. So we can make this into a Grignard reagent. In this case, I added formaldehyde to make the alcohol, and this is still the silyl ether. What do you do next? Remember, after you do a Grignard, you dump it into acid, don't you? Turns out that when you dump this into acid, the silyl ether falls off. and holy capoly, you've made your desired compound. That's kind of neat. The other strategy is a little more elegant. It's called the dihydropyranyl ether. Turns out that if we take an alcohol in the presence of dihydropyran, this stuff, oxygen double bond, and acid, we can make an ether like this. Now this might seem like magic, but what's really happening here, if we dump this back in acid, it falls off. So that's where we're going here. Why does this work? Because in the presence of acid, we're going to protonate the dihydropyran, and we're going to make this carbocation, this resonance stabilized. Once we have this, the oxygen can attack. When it attacks, we get this stuff. Now in chapter 19, we will learn that this is called a ketol. The neat thing about ketols is you dump them into acid and they fall apart. You get your alcohol back where you started. Do your reaction, add acid, and you're back to where you wanted to be. It's amazing. So if you have an OH group that's a bother to you, there are two simple strategies we can do to protect it. Any questions? All right. Let's finally, we're talking about alcohols. If you look on the periodic table, what's directly under oxygen? It's sulfur. An alcohol is an OH group. A thiol is an SH group. Thiol is also called a mercapto group. You don't have to worry about the nomenclature here, although we'll show it. The one thing that you need to remember about thiols is that they stink. They stink. The essence of skunk is a set of compounds in their spray consisting of mostly these guys. And they stink. When I was in graduate school many years ago, I had a good friend who worked on, benzene thiols. So a benzene ring with an SH attached. Chuck was his name. Nobody ever wanted to talk to Chuck because Chuck really stunk. I mean, he was careful as he could be with everything that he did, but somehow this stuff got into his body and it just came out for the next number of years. It was amazing. These are thiols. Again, they have the SH group and they stink. An example of the nomenclature. Here we have 4 carbons. We'll call that butane thiol. Cyclohexane thiol, benzene thiol. This was the bad guy. If you do biology, I worked in biochemistry for 40 years. Okay. When you do electrophoresis of proteins, you have to reduce the disulfides. You do that by adding mercaptoethanol. That stinks too. Not as bad as benzene thiol, but it does stink. So you have to be real careful if you do this sort of stuff. To make thiols, very simply, you can do it by an SN2 reaction. Sulfur is a wonderful nucleophile. As you go down the periodic table, the nucleophilicity increases. Much better than oxygen. Simple SN to attack, and you make your thiol. Very, very simple. A more elegant way that doesn't involve quite as much stench is to use an alkyl-thioronium salt. This is called thiourea. Urea would just have an oxygen here, this has a sulfur. Turns out this is a good nucleophile also. You can add it, form the isothiuronium salt. When you dump this into base, this part is gone as urea, and you're left with your thiol. It's a little bit friendlier. Finally, we talked about electrophilic aromatic substitution and nucleophilic substitution, which may still bring back memories from the last exam. Turns out that because sulfur is such a great nucleophile, it is a real champ at doing this type of chemistry. Sulfur attacks the ring, you form your addition intermediate, chloride leaves, and you're left with your thioether. Any questions? This pretty much does end chapter 17. Now, let me just nag one last time. Some of you have not quite finished the reaction thing for lab reports 2 to 5. That's 40 points. Don't blow that off, okay? After you do your 40 points worth, look at your point total. If it is 150 and above, you're doing A1, and you're good. If it's less than that, well, then we can talk. But if it's 150, you're good. We have spring break. That's good. We'll come back, instead of having lab our first